Hello, welcome to another module in this massive open online course. We are looking at discrete time Markov chains and the analysis of discrete time Markov chains, essentially characterizing their properties using the one-step transition probabilities, built the transition probability matrix, and also looked at a couple of examples. Now, let us continue our discussion further. We were looking at, for instance, the industrial reliability or the machine reliability example, where we have an operating machine and that can be in two states, that is operational or faulty, and it can transition from one state to the other. So, you look at the state at the beginning of each hour, so it is either operational or faulty. By the next hour, it can either continue to remain operational or faulty, or can transition from operational to faulty or faulty to operational, right. So, let us continue our discussion on that. So, basically we are looking at DTMCs, right, that is your discrete time Markov chains, not to forget. That is stochastic processes with the Markov property, right. And we are looking at the industrial reliability property, the example of industrial reliability, right. So, we are looking at this example of industrial reliability where the machine can be in one of two states, right. So, the machine, a particular machine or device can be in one of two states. It can either be operational, which I will call as the state O, or it can either be faulty, which I will call as the state F. And the various transition probabilities are the transition from operational to operational, that is it continues to remain operational, is 0.95. The probability that it goes from operational to faulty, that is 0.05. The probability that it goes from, if it is faulty, it continues to remain faulty, is 0.1, and the probability that if it is faulty, it transitions to operational, is 0.9. That is, and these are what we called as the breakdown. This is the probability of, for instance, breakdown, and this is the probability that faulty to operational, this is the probability that it can be repaired within the hour, that it breaks down and it is repaired by the next hour. So, it goes from faulty to operational. Now, let us extend this example to two machines. So, the general question might be, so we have considered a simple example with one machine. Now, what happens, let us say we have two machines operating independently, then how can you model this system, what would be the states, and how do you characterize the transitions, right. So, now consider two machines, consider the industrial setting, because typically in industry you have several such machines, and naturally we would like to generalize this to, let us say, two machines, and the key here is that these are independent. That is, their operation is independent, that is the problems occur independently, they break down independently, and because the problems are independent, they can be that the probability that they are repaired or not being repaired is also independent, right. And we know from probability theory that if two events are independent, then the probability of A intersection B equals probability of A into probability of B. This is for independent events. This is for independent events, right. Now what does this mean? Now let us look at, now let us first characterize the state space for this problem. What is going to be the state space? Right. So these machines are similar machines and their operation is independent. Now since these machines are similar, we do not care which particular one of this is operational or faulty. Let us say there are two machines, if either one of them is operational, then the purpose they serve is the same. So we can characterize this by three states, that is operational, both are faulty, or one of them is operational and one of them is faulty. It does not specifically matter which one is operational, which one is faulty, because essentially the output of each machine is the same, right? The operation characteristic, you might say, or the output is same, all right. So the state space can therefore be modeled as follows. The S can be modeled as S0, S1, S2, where S0 is both are operational, one is operational, other is faulty, and both are faulty. So this is basically both operational, this is both faulty, this is both faulty, and this is essentially one operational, other faulty. This is a state where you have this is a state where you have one operational, other faulty. Okay. And therefore, so you have both operational or both working, S2 is both faulty, one operational, other faulty. As I said, we do not specifically care about which one is operational, which one is faulty, okay, because both machines serve the same purpose. All right. Now let us find out what the transition probability is. Now let us remember, to characterize the DTMC, we need the transition probability, or the one step transition probabilities. We need the one step transition probabilities. What are these one step transition probabilities? Let us look at probability, start with probability xn plus 1 equals S1 given xn equal to S1, that is both are operational and both continue to remain operational, right? Both are operational and both continue to remain operational. What is the probability of this? Probability of this is, remember, operational, both continue to remain operational, that is, you can say it is operational intersection operational, that is both continue to remain, continue operational, intersection continue operational. So if you think of continue operational as the event CO, right? So this will be probability of continue operational 1, CO1, that is machine 1 continues to be operational, machine 2 continues to be. So you can think of machine 1 continues operation and machine 2 continues operation, and this would be which, as I said, if these, since these machines are independent, now this becomes the product of these probabilities. That is the interesting thing. So, this becomes continues to be operation 1 times the product continues to be operation 2. So, this is because the product is because of the independence. And this becomes your 0.95. remember, that is a product probability that machine 1 continues to be operational, 0.95, probability machine 2 continues to be operational, the product is 0.9025. So, P11 equals 0.9025. This is a product probability that xn plus 1 equals S1 given xn equals S1. Let us compute one more. We will not compute all of them. I will just illustrate the general procedure and you can extend it to the other transition probabilities, right. So, let us for instance look at another thing that is slightly different. Let us look at P of 3, 2. That is the probability xn plus 1 equals S2 given xn equals S3. That is basically it goes from both faulty to one is operational, it goes from both faulty to one is operational, other is faulty. Now, remember in this you have two machines M1 comma M2. So, in this operational faulty you can either have one of them is working, the other is faulty, either M1 is operational, M2 is faulty, or M2 is operational, M1 is faulty. Okay. So, both of them. So, OF basically encompasses both of them. So, FF to OF can occur. So, this occurs. So, if you analyze this, FF to OF occurs if M1 goes from faulty to operational, that is M1 is repaired, while M2 continues to remain faulty, that is M2 goes from faulty to faulty, M2 is not repairable, or that is M1 cannot be repaired, continues to remain faulty, and M2 goes from faulty to operational. Now, these two events, these two are mutually exclusive, so their probabilities can be added, and now these two are independent, right. Now, this probability is going from faulty to operational, that it can be repaired, this is 0.9, faulty remains faulty, this is 0.1, faulty remains faulty, this is 0.1, M2 goes from faulty to operational, this is 0.9. So, therefore, this net transition probability you can write it as follows. This is probability M1 repaired times probability M2 continues to remain faulty plus probability now M2 repaired cross probability M1 continues to remain faulty. And this product, once again, this arises because both these are independent, right. Not to forget that the probability that M1 is repaired and continues, because the problems occur independently and the probability that they can be repaired, these two events are independent. M1 is repaired does not mean that M2 can be repaired, M2 being repaired does not have a bearing on M1 being repaired, alright. These two are independent and therefore, we multiply the probabilities, alright. and so therefore, this is equal to now probability M1 repaired, this is 0.9, probability M2 continues to remain faulty is 0.1 plus probability M2 repaired 0.9, probability M1 continues to remain faulty is 0.1. So, this is 0.09 plus 0.09, that is 0.18. This, remember, is the probability that is the probability xn plus 1 equal to S2 given xn equal to S3, and therefore, now you can similarly compute the other transition probability. So, I will simply add here similarly compute other transition probabilities. Now, recall for this problem we have 3 states, right. So, if you look at this problem with 2 machines, we have n equal to 3. So, we have 3 states. This implies the matrix P is of size 3 cross 3, transition probability matrix P, this is of size 3 cross 3, and this matrix will be given as, and you can verify this will be given as 0.9025, 0.095, 0.0025, 0.855, 0.14, 0.005, 0.81, 0.18, 0.01. This is essentially the transition probability matrix, which is a 3 cross 3 matrix for this problem, for this industrial reliability problem with 2 operating machines which are operating independently, 2 similar machines which are operating independently. So, essentially now you can get an idea of how to construct more and more complex problems and complex examples, starting with a simple example. Okay. Let us look at another example. The TTMCs have a large number of applications such as I have already told you inventory management, so on and so forth. Let us look at a simple example. Remember, we also talked that stock price prediction. So, let us look at the stock market. So, let us say the stock price, daily stock price we characterize this as the state. This can be either, let us consider a simple example, although you can build more complex examples starting from this 100, 200, 300, 400, 500, and let us call these states as S1, S2, S3, S4, S5, and now each day either of things can happen. We monitor the stock price every day, either at the beginning or at the closing. Each day either decrease by 100 with probability equal to 0.2, or the stock price can increase by 100, probability equal to 0.2, or it can remain constant. Or remain constant, probability equal to 1 minus, I will simply say other probabilities, because there is a catch here. What is the catch? The catch is whenever it hits the maximum 500, it can only decrease, it cannot increase, alright, or whenever prices hits 100, it cannot decrease, it can only increase. Okay. So, that is the catch. So, what is the catch? At price equal to 100, only increase, price equal to 500, we have only decrease. Okay, price equal to 500, it only decreases. Okay. Now, what do we do? Therefore, now let us take a simple example. Let us ask what is the probability x n equal to, let us say 400, or x n equal to S4, right, x n equal to S4 given, or we can say x n plus 1 equal to S4 given x n equal to S3. Remember, S4 means price is 400, S3 means price is 300. Probability price increases from 300 to 400, that happens with probability of 0.2, right. Similarly, what is the probability x n plus 1 equal to S3 given, or given x n plus 1 equal to S3 given x n, let us continue on the S4, x n equal to S3, or let us say S2, that is, remember S2 is 200, S3 is 300, probability that decreases by 100, this is equal to 0.2. Now, one can ask what is the probability x n plus 1 equal to S1 given x n equal to S3. Now, these are basically your probabilities 3, 4, I believe probability is 3, 2, this is probability 3, 1, this is equal to 0, because remember this is essentially your 100 and this is essentially your 300, it cannot fall by 200. So, this is equal to 0, P 3, 5 similarly equals 0, probability increase from 300 to 500, that is 0, and therefore, now if you look at this probability x n plus 1 equal to S3 given x n equal to S3, remember all the probabilities have to add up to 1. So, this is 1 minus 0.2 minus 0.2 equals 0.6, alright. So on and so forth, you can compute all the transition probabilities, and therefore, the transition now look at this again, there are 5 states. So, n equal to 5 states in this DTMC, therefore, we have the transition probability matrix P is 5 cross 5 matrix, and therefore, this can be written as follows. We have already computed the third row, row number 3. So, that is going to be 0, 0.2, 0.6, 0.2, 0, and remember I am just going to write the prices over here 100, 200, 300, 400, 500, and these are also 100, 200, 300 what we have just written, 400, 500. Now the probability it goes from, again let us look at the 200 probability, it goes from 200 to 100, it decreases by 100. So, this is again 0.2, probability remains at 200, you will see this is 0.6, this is 0.2, 0, 0. Similarly, from 400 to 100 it decreases to 100, that is 0, it cannot decrease to 100, it cannot decrease to 200, it can decrease to 300 with probability 2, it can 0.2, it can increase to 500 with probability 0.2, remaining is probability it stays at 400, that is 0.6. Now, what about these are the interesting cases, what about the 500? Now, at 100 remember it can either go to 200, but it cannot fall to 0, remember that is not one of our states. So, the remaining, so all the other probabilities are 0 and the accumulated net comes into 100, that is this becomes 0.8, remember 1 minus 0.2 because the sum of each row has to be 1. So, probability it remains at 100 is 0.8 and probability that it goes to 200 is 0.2. Similarly, at 500 it cannot go to 600, so it can only go to 400, this probability is 0.2, rest all are 0 and this is 0.8. So, this is 0.2, so this is 0.8. Okay. So, and this I believe is our 5 cross 5 transition probability matrix for the stock price problem, and this is a simple problem, and this idea is this can be used to build more complex problems. So, this is the one step, this is the transition probability matrix. This is the transition probability matrix for this problem. Alright, so we have looked at several interesting examples, variation of original examples and also interesting example pertaining to stock price. So, as you can clearly see, DTMC is a very powerful framework which has several applications, be it either reliability, industrial, what you call as the health monitoring of machines, or be it stock price, stock market modeling. I already told you about inventory modeling, prediction, inventory management, insurance. There are so many areas, again one of the very powerful frameworks. It can also be related, more complex models can also be built for stock markets, financial mathematics and futures and derivatives, and that is basically how is the stock price evolving, what is the price of a future, what is the price of a derivative, and all these kind of complex questions can be readily answered using this framework. So, clearly a very powerful framework. I urge you to once again go through the lectures to understand and appreciate all the concepts completely. Thank you very much.